So we have that xt equals 15 plus 1.8 times t plus 0.6 t times at. And we'll note here that at is random. It's the noise term. It's random and it's distributed normal with mean 0 and standard deviation 1. Which recall that that also means it has variance 1 because the variance is the standard deviation squared, the standard deviation is 1, and 1 squared is 1. So what we'd like to show is first that mu xt equals 15 plus 1.8 t, and then we'd like to show that sigma xt equals 0.6 t, where sigma xt is the standard deviation of xt, and so if it equals 0.6 t, we would show that the standard deviation of xt depends on time. So let's start off with a few identities. So we have the expected value of c, where c is a constant, is equal to c itself. So the expected value of 7 equals 7. And that mu at, the mean of the noise term, is equal to the expected value of at, of course. And the expected value of at is 0 because that mean is 0, right? Mu at is right there. That's the 0. So just reminding ourselves of that fact. And then finally, remember this is the standard deviation, but it's also the variance since it's 1 and 1 squared is 1. So the variance of at, we should put on here, we know equals 1, and that is equal to the expected value, just to remind ourselves of the variance equation, or one variance equation, is the expected value of at minus mu at squared. So, great. Let's start with number 1. So we would like to show that mu xt equals 15 plus 1.8 t. So we'll start with mu xt equals, by definition, the expected value of xt, which equals, in this case, the expected value of 15 plus 1.8 t plus 0.6 t at. Great. And that's that. So now on the next line here, we'll use some of our identities. We'll use this constant identity. First, we'll break it up. So we'll say this is equal to the expected value of 15. Ooh, there's a constant. Plus the expected value of 1.8 t. T is not random. T is time. Plus the expected value of 0.6 t at. Okay. So let's do a little bit more here. We'll take it step by step. So that's just 15. The expected value of a constant is 15. 1.8 t. T is constant. T is time. So that is plus 1.8 t. And then plus, we have a rule that says, hey, those constants can come outside of the expected value. So that's 0.6 t times the expected value of at. And we know that the expected value of at is 0, so that term just goes away. So that will equal 15 plus 1.8 t plus 0. And so we've done it. Mu xt is equal to 15 plus 1.8 t. We've got number 1. So now we're going to come over here and do number 2. Probably write a little smaller. We've got some work to do. But what we'd like to show is that sigma xt equals 0.6 t. So I'm going to start this time actually with the variance. So I'm going to say that the variance of xt, and we'll see why we're going to do that. But we have here, we have this nice definition. The variance of anything equals the expected value of that thing minus the mean of that thing squared. So this will just be equal to the expected value of xt minus mu xt squared, and that's that. That's what it equals. So this will equal, so I'll go here to here and then come back to here. This equals the expected value of, let's expand xt. Xt is 15 plus 1.8 t plus 0.6 t at, and we just established the fact that mu xt is 15 plus 1.8 t. So that's 15 plus 1.8 t. And of course we want to square that, and that's what we have. So luckily some things simplify here, and we get the expected value of So that'll be 15 minus 15, so that's gone. That's 1.8t minus 1.8t, distributing the negative sign, so that's gone. And we'll just be left with the expected value of 0.6t at squared, of course, squared. And that's what we have so far. Great, so let's square it. So that will equal, make sure we've got plenty of room down here, so that equals the expected value of 0.6 squared, which is 0.36 times t squared times at squared. Okay, so that's what we have so far. Awesome, so we have these constants, right? 0.36 t squared, so that's going to equal 0.36 t squared times the expected value of at squared. Great, so let's go back to our identity and make a special observation. And that observation is, remember that mu at is equal to 0. So this is the expected value of at minus 0 squared. So that's the expected value of at squared is equal to the variance of at, which is equal to 1. And there it is, the expected value of at squared, that's just this. This is the expected value of at squared because mu at is 0. So this I'll rewrite just to be super clear what we're doing. 0.36 t squared, that's the same as the variance of at. Again, because of that, because mu at is 0. And so if we have that, then the variance of at is just equal to 1. And we see that this equals, then this equals 0.36 t squared times 1, because now that's equal to 1, which equals 0.36 t squared. So we have here that the variance of xt equals 0.36 t squared. That means that sigma, again just using notation, sigma squared of xt equals 0.36 t squared. And thus, sigma of xt equals the square root of sigma squared xt, which equals the square root of 0.36 t squared, which equals 0.6 t. And there we have it. Sigma hat xt is equal to 0.6 t. That's what we wanted to show. Great job.